Good morning. I'm Chris Hewitt. I'm with the ISC's Engineering and Research Department. Glad to see you guys here. I'm glad you survived the honky-tonk highway and made it up at 8 a.m. I'm proud of you. We have two great speakers for you this morning, so we won't disappoint. They're both from the University of Toronto, hence the CN Tower on the screen there. Our first speaker is Constantine Christopoulos. He received his PhD from the University of California at San Diego, and did his undergrad work in Montreal at the Polytechnic University. He's now at the University of Toronto teaching seismic damping, right? Seismic isolation of steel structures. And he's recently co-authored a book on principles of supplemental damping and seismic isolation. And then our second speaker will be Jeff Packer. Jeff is also from the University of Toronto, did his undergraduate work in Australia, and then has his PhD from the University of Nottingham. Jeff's best known for his work on HSS connections and HSS members. He's authored a number of the CDEC design guides, which are geared more toward that industry. And it's going to be our upcoming co-author on an AISC design guide on HSS connections, which we expect out in the next year or so. So please welcome these two excellent speakers to the stage.
Thank you for the introduction. Thank you for showing up this morning. So we'd like to talk a little bit today about seismic design of ductile special concentrically braced frames. And I think part of the lecture today is really to try and perhaps convince some of you who are not too excited about doing seismic design and ductile design that this is really something that is available, and it really has really good reasons why engineers should be moving towards these types of designs, especially in steel. We have inherent ductility, and we should take advantage of that. So our presentation will introduce ductile seismic design, some basic principles, seismic behavior of ductile steel brace frames. How do we apply this seismic ductile design philosophy to steel brace frames? Then we'll look at an overview of two designs, one in Los Angeles and one in Boston. Obviously the seismicity is different, so we'll see what comes out of these two designs following ASC 7 and LRFD AISC 05 for the detailing. And then I will switch it over to my colleague Jeff Packer, who will be talking about the HSS connection in the brace design that we've carried out. And then we'll bring up a lot of issues about how do we actually build, fabricate, detail these braces so that they can achieve what we're expecting out of them. And finally, he'll introduce a novel system that had been developed and tested at the University of Toronto that greatly simplifies all these connection issues that he'll be discussing. So just starting at the start here, in structural design, this is something that we don't really look at unless you're looking at seismic loads. And there's this question about if you keep on loading your structure, what will fail first? Okay? Obviously, when we design structures to remain elastic, that's irrelevant because nothing has to fail, nothing has to yield. But when you're looking at a seismic event, you know that during this seismic event, something will yield or fail. So the question is, which one? Now, these links here symbolize the different aspects in the structure. This could be the foundations, the braces, the slabs, and when you pull on a link that's all interconnected and you have no idea what's the weakest part of this, you don't know what is going to fail. And when that happens, basically you can get undesirable failures and collapses. So the other thing we should keep in mind is when you get your manual ASC and you look at the seismicity for all over the US, one thing you should keep in mind, it looks very nice, very colorful, but there is huge uncertainty on the definition of the ground motion. So the earthquake that may hit your structure may be significantly larger than the one you've designed for. So keep that in mind. This is not a deterministic and very well established loading condition. So how do we protect ourselves against this? So we take those links and we put them in order, and we make sure that we know what the weakest link is. And that weakest link is going to be an element that we will detail to remain ductile, and while this is yielding, basically the bracing members portrayed here in this picture. Everything else is oversized with respect to the capacity of this member, which allows then all of these other elements to be protected. What does this do for the response of the structure? What it does is it's going to yield, it's going to deform inelastically back and forth, but it will not collapse. The integrity of the structure and its ability to carry gravity loads will not be compromised by the fact that you are overloading the structure. So what are the benefits of using ductile design? So if you can actually design a system that can exhibit a good ductile response, it can basically be designed to resist seismic forces that are significantly lower, and we'll see the system we're looking at today, an R factor of 6, which means we're going to design this building for loads that are 6 times smaller than the actual loads that you would expect during an earthquake if the structure were to remain elastic. So you can do that safely, and obviously this can be an economical design as well if you're reducing your loads by a factor of 6. And if you can allow this structure to undergo stable and elastic deformations, you will get a very good seismic response, and the structure will withstand this earthquake. And this is really the concept around which modern seismic codes are all hinged around, developing this ductile mechanism and making sure that it remains stable. So the other thing is, when you have ductile design, when you pull on a yielding element, when you yield it, if you keep on pulling, the forces don't go up. You get inelastic deformation, but the forces don't go up. So if the earthquake is slightly larger than the one you designed for, and you have a proper ductile design, what's going to happen is that the structure will deform a little bit further, and you want to build in that capacity into your structure, but you don't want the forces to go up in all the elements and then get unexpected failures because the loading was greater than the one you assumed in the design. So this is a major advantage, and always keep in mind the uncertainty behind ground motion. So behind this whole concept is an equal displacement approximation. When this came out, it was called a rule in the 1960s. Veletzos and Newmark are professors here in the US who basically observed the following, that if you take an elastic structure and you run an earthquake on it and the structure is infinitely strong, what will happen is you'll develop a base shear, or the force you need to design the structure, of V elastic. If you actually design the same structure with the same stiffness, but to yield at different levels that are below this maximum force, what will happen is this structure will basically yield and undergo cyclic loading, and if it doesn't collapse, what will happen is it will have a maximum displacement that will be similar to the one you got for the elastic system. And they observed this in the 1960s, and this is really the basis of what we call force-based design and of all modern seismic codes. Okay? So what we're going to do is, you can see here that if you design for something that's slightly lower than VE, you have to develop this level of plastic deformation. And plastic deformation is measured as a ratio of the maximum displacement divided by the yield displacement, and that is displacement ductility, mu delta here. So if you design the structure for a much lesser load than the one it would see under elastic, if it was elastic, what this means is you need to provide more ductility. So remember I mentioned this R factor of 6 we're going to look at for brace frames. If you use an R factor of 6, you have to be able to provide ductility that is equivalent to approximately 6. If you use an R factor of 1.5 or 2, you only need to provide that amount of ductility. So it's very important when you reduce the loads, you have to make sure that the system you design is capable of giving you this level of ductility. So what are the principles of seismic design? No matter what system you're defining, these are the main steps you have to go through, and we're going to go through them for a concentrically braced frame. So the first thing is you need to clearly define what the seismic force resisting system is. Okay, you can't say, well, I've got a couple of frames here and a couple of walls there, and it's somehow going to, you really need to say from the start, my seismic resistance system is going to be a brace frame or a moment resisting frame or whatever you decide to use. Then you need to define a load path from all elements that have a mass all the way to the SFRS. Okay, an earthquake loading is not forces, it's the ground shaking. And the ground shaking multiplied, the acceleration of the ground multiplied by the mass creates inertia forces. That's your loading. So wherever you have mass, you're basically going to generate forces, and typically in a building, the center of that force is going to be the middle of your diaphragm. So if that force doesn't have a load path to reach the perimeter frame where your braces are, you won't be able to withstand these loads. Okay, so you need to establish a load path and make sure these loads carry over all the way to your lateral load resisting system. Then we're going to design this system, the seismic force resisting system, for a level of strength that allows us to get inelastic response, but also to control displacement so that the structure doesn't become unstable during the earthquake. After we do this, since we are designing for lower forces than the ones we expect during an earthquake, we need to make sure the system has ductility. How do we do this? It's detailing. Okay? It's the choice of the members, the properties of the members. We want to make sure they can undergo repeated inelastic loading during the earthquake. Once you've designed the elements that are going to yield, you then reverse and you design everything else in your structure to remain elastic when these elements are yielding. Okay, so that is the basic strategy that we apply no matter what kind of seismic design you're going to be carrying out. So the way it works is we assume and we look at the properties of the structure and we come up with the elastic base shear, which is how strong would this structure have to be if it were to remain elastic during this earthquake such that it could safely resist this earthquake elastically. And that's VE. And we'll see how we get that from ASCE. And then, depending on the system we use for our seismic resistant frame or system, it's going to give us an R factor that we're allowed to divide this elastic force and design for a significantly lower force for our system. So now, how does all of this relate to brace frames? Okay, so this is how a brace frame is supposed to work if you design it properly. When the seismic loads push laterally on this frame, what we're expecting this system to do is to have tensile yielding in tension here in the tension braces and compression inelastic buckling in the compression brace. Okay, and I know buckling is a scary word, but this is controlled inelastic buckling. The way it works is you get a hinge here that forms on the two extremities of your brace and one in the middle. And if this element is designed properly, it can do that over and over. It buckles inelastically and goes into tensile yielding for 20, 30 cycles. And that's how you reach a ductile system. Now what I want you to realize is that when you push on this system and this yields and this buckles and you have pin connections or very little moment connectivity on your frame, this system is a mechanism. You can push it over with no additional force. There's nothing resisting the earthquake. Okay, so when that happens, these forces cannot go higher. So what does this look like? Here's a test in a laboratory that we'll be talking about a little bit later. But this is a buckled steel brace. This is a hinge up here, another hinge in the middle, and one down here. And here is what it looks like when you pull. This is tension and this is compression going down. And what happens is you get tensile yielding, so you'll go up and you'll yield, and then when you come back you'll reach the peak compressive force, and then it'll buckle, and then this load will go down as your second order member effects kick in. Okay? So this is really the behavior that we want to try and design for and achieve. Now the question, how do you make sure this brace doesn't fracture when you start yielding it in tension and buckling it in compression? What makes this system ductile? So there's two parameters for the braces that are very important. One is the brace slenderness, and the other is the section slenderness. And these are the two parameters you need to control in order to get good ductile response. So if you have very high slenderness, what happens is your hysteresis, or the energy that the member dissipates, becomes so low that you don't get a desirable seismic response. If your slenderness is too low, what happens is you basically will fracture the brace at a much lower ductility. Okay, so you need to balance this. And currently, the limit is on the upper bound, which is that the KL over R has to be, this is wrong here, smaller than 200. Sorry about that. This should be here. So your KL over R, your brace slenderness should be lower than 200. And with research that is currently going on by Tremblay and others, there might also be a lower limit that will be introduced soon. So anywhere between 70 and 200 is a really good range where you can get good brace behavior for seismic applications. The next thing is the section slenderness, and this comes in the form of B over T and D over T limits, and you've all seen these for other applications. The reason why this is important, if the wall of your yielding member is really small, what will happen is when it buckles, it'll basically concentrate all of the rotation over a very small distance, and it will quickly, like a paper clip that you go back and forth with, it'll fracture at that location. So you really need the walls to meet these B over T and D over T limits, and these will be discussed in more detail by Jeff Packer a little bit later. Now, one thing that's very important is all of this that we've just discussed is really fairy tales if you can't connect your braces. Okay, so if during this seismic response you're expecting this thing to go under tensile yielding and compressive buckling back and forth, and in the middle of all this you basically fracture a connection, then the whole system is gone. Okay, so very careful detailing of connections, and we'll see this is not trivial to develop the connections that you need to carry these types of loads, and these will be covered as well by Jeff. Okay, so let's look at what happens here with the effect of slenderness. This is a slenderness of 142. And you can see here what I mentioned is the pinching. So the first cycle you yield, and then you come back, you buckle, and you go out here. Then the next cycle you have to, the brace has gone longer. When you yield in tension, it buckles. And then the next time you want to go back, the brace is a little bit longer. So it has a bit of a slackness in it. So that's why the next cycle we go further. But you can see here that with 142, you get a much larger ductility than you do with a slenderness of 93, KL over R of 93 here. But on the other hand, look at the area underneath these curves. You dissipate much more energy. So this is a better system in terms of the damping that it provides to the structure. So in general, you'll get more ductility capacity, so the brace can undergo larger inelastic deformations for larger KL over Rs, but we have to be careful not to go beyond 200 because it becomes too pinched, and then we don't dissipate any energy during the earthquake. And here is the compactness for a W section. What happens here is if you look at the B over T of 9.9 or 5.9, we can see here that the same brace basically fails much earlier when you don't respect this B over T limit, or where you have a higher B over T limit. And this is why we control the section slenderness during the design of these braces. Okay, so let's take a look now at how this is applied in the seismic codes. And let's look at the design of a pretty regular building. And we're going to design the exact same building in Los Angeles and in Boston. And obviously, in Boston, the seismicity will be significantly lower, as we will see with the Spectra in a couple of slides. And after doing some preliminary assessment of this, we realized that the forces in the Los Angeles brace frame are so high that it becomes really non-practical to leave one braced bay, so we split them up into two. So the Los Angeles building will have brace frames here and here, and the Boston, you can get away with a single one here. And again, for brace frames, it's not only the cost of your braces and all that, you have to look at the forces you're imparting to the foundations. That could be a very expensive aspect of seismic design if you have to carry very large tensile forces that are generated by your braces. Now, here you have to realize that this entire building relies on these perimeter frames for seismic resistance. And the reason for that is this requires a lot of detailing. It's kind of expensive, so people have moved to these perimeter seismic resistant systems. Okay, and that's fine as long as, remember what we were saying previously, the centroid of the seismic force is somewhere here in the middle of this diaphragm. These loads need to find their way all the way out here. Otherwise, there's really no use in designing this if all of this load doesn't make its way to the CBF on the edge. So here is the seismicity map for the US, and you can see the difference here. I can't see it here. There's LA and Boston, so you can see a major difference in the seismic accelerations, and we'll see that when we derive the spectra for these two sites, the same difference will appear. So if we now look at SCBFs, they are the most ductile concentrically braced frame system that the code will allow you to design. You need careful detailing because you're using this large R factor. You're designing for much less force than what your elastic forces would have been. So you need to make sure that the ductility you're assuming the system has is built in to your design. And we'll talk a little bit about these. It has an R factor of 6, an overstrength factor of 2, and a displacement factor of 5. And I'll get back to these a little bit later. And what we did here is we use an inverted V-brace system. And we'll see if you use a chevron brace system, basically, you have to be very careful that the beam is designed properly, and we'll look at how we do that. Otherwise, your beam will yield under the unbalanced force between the tensile yielding brace and the compression brace, okay? So if you go into your ASCE document, here's where you'll find the special steel concentrically braced frame, and those factors I was just talking about, R equals 6, omega naught, the overstrength 2, and the displacement factor 5 can be found there. And you see the height limits, no limit for seismic areas B and C, sort of lower seismicity areas, or the categories, and then for the larger seismic categories, you have a limit of 160 feet. So the next thing you need to do is to start the process. You need to build the spectrum for the sites, and that will give you the level of the seismic loading that you're going to be using in your designs. So looking into your ASCE document, you can basically find these parameters, the short period spectral acceleration, the 1 second, and then the long period definition here. And for Boston and LA, these are the values that you get. And with these values, you can build the response spectra that you're going to be using for your design, or your design spectra rather. And look at the major difference that you get between Los Angeles and Boston. So now the next step is you have your basically your spectrum, and you have to start the design now. So the first thing you're going to do is you're going to use the static method of design, which is a simplified method that allows you to get preliminary forces to size your members. So the first thing to do this, the seismic loading is dependent on the period of your structure. So you're going to estimate the period of your structure using an empirical equation of the form TA is equal to 0.2 times the height of your building to the power of 0.75. And this estimate gives us 0.442 seconds. Now, if you look at the spectrum here, the code, if your real period is likely to be around here, the code empirical equations are always underpredict or underestimate your true period. So what's going to happen is if your real period is 0.8, you would get this acceleration for design, and the code will probably tell you your period is 0.4. So you'll be designing with the static method for roughly, in this case, maybe 2 times more load, okay? What that does is it forces you, if you don't go and do a more advanced response spectrum analysis later, you're going to be stuck designing your building for these higher loads. But it allows you, if you complete your analysis and do a dynamic analysis using response spectrum and modal analysis, it allows you to go back to a more realistic level of seismic loading. So obviously you cannot really design economical structures just by using the static method. You really want to go take advantage of what the code allows you to do. So if you carry out this calculation, you basically get this period. And because we are going to do a dynamic analysis, we know that we're going to be capable of proving that our period is longer. So we take advantage of the maximum period that the code allows us to use, which is 1.4 times the period that you get with this empirical equation, and 1.7 times for Boston. So if I can prove that the period of the building in Los Angeles is longer than 0.619, I'm allowed to use this period to establish my seismic loads. Same for Boston here. But we have to come back later and show that that is really the case. So in terms of the other loads that we use, they're pretty typical, and you can take a look at them here. I think it's pretty standard type of loading, and obviously we are assuming that it's similar type of load for both, except for the snow load in Boston that we don't have in Los Angeles. Okay, so once you get your period that is computed from the empirical method in the code, we basically take advantage of the elongation of the period that we're allowed, 1.4 for LA, 1.7 for Boston, and then we want to compute this seismic factor in order to get our design-based shear. And the way you do this is you basically just take the spectral acceleration here and you divide it by the R factor. For this system is 6. And this is the importance factor. We'll use an importance factor of 1 for both of the buildings. If the building is a critical building that must remain operational after an earthquake, a hospital, etc., then the importance factor will go up. But we can assume that it's a typical building with I equals 1 here. So if you carry through this calculation, what you'll find is that you get base shears of 1,602 kips for Los Angeles, and 154 kips for the Boston building. Okay? And this is once again obtained from the static simplified method in the code. So the code, to allow you or to encourage you again to go to a dynamic, more refined analysis method, further allows you to reduce the seismic loads to 85% of these static base shears that we obtained here. And in order to do that, you need to carry out a response spectrum analysis to prove that in fact it is lower. And it allows you to reduce it by 15%. So if the base shear that we compute through our dynamic method is less than 0.85 times V, we need to scale everything up to this minimum of 0.85 V. Okay? Which is not a problem because the analysis is linear elastic, so whatever you get, you scale it all up linearly to 0.85 V. So we're assuming, we're very optimistic because we've done this a few times, so we know that when we're going to do the dynamic analysis, we will be able to prove that basically we can go all the way to the limit of 0.85 V. So in our initial design, we'll assume this, and we'll design for this reduced base shear of 1361 kips and 131 kips for Boston. And we will confirm this later with our dynamic analysis. Once you have the base shear, that's the total base shear the structure resists. You have to distribute that along the height of the structure in order to design your different story shears and size your members. So how do we do that? The code gives you an equation. If you look at this equation here, the force that you apply at every level X in your structure is proportional to the weight of that floor and the height of the floor. And you have this power here, K. And if you look at the expression for K, it should say here that K is basically 1 or greater. So if your period is less than 0.5 seconds, you have a very short structure. You don't have any higher mode effects. You don't have to amplify the forces at the top of the building. So it's linear. If you put K equals 1 here, this gives you an inverted triangular linear distribution. If K starts becoming greater than 1, then you basically get a larger portion of the base shear applied at the higher floors, and that's done to basically simulate the effect of higher modes. Okay? So this is a very easy equation. With your base shear, you distribute it, and you get the forces per floor. Now, one thing you have to take into account is during an earthquake, if you get a torsional response, that will amplify the forces that you're designing your lateral load resisting system for. And so you have to take into account torsion. Now, because our building is symmetric, the mass center of mass is close to the center of rigidity for this building, we don't have any real defined eccentricity, but the code forces you to assume that there will be a 5% of the dimension of your building accidental eccentricity. So how do you do this? You look at the dimension of your building and the dimension that you're actually working on. You move the point of application of the seismic force by 0.05, 5% of this. And what this does is it will create a torque that will turn your building. And how is that torque resisted? It's resisted by additional shear in this direction down here and a reduction in the shear on these walls. That's how torque is resisted. And if we had our perpendicular elements, they would also help us in torsion as well. So one way to do this, which is simplified for this stage of the calculation, is to just look at how much larger do these forces have to be in order to withstand this additional torque that is being resisted. And you'll find if you do the calculations that it comes out to about a 10% increase in the seismic lateral forces. So we take this into account to make sure that when we do a more refined analysis, our structure isn't under-designed. And the other thing you need to take into account is when a building undergoes seismic loading, you get lateral deformations, and at the same time you have gravity loads that are applied to this building that will tend to basically amplify these deflections. Okay, second order effects, this is sort of what we do for the design of frames anyway. Because in seismic loading we expect larger deformations, we should look at this. So the way you take this into account, you can look at this equation here, which has the theta story stability ratio. And basically what you're looking at is you take a floor, you look at the deformation of that floor, you take the weight, all the weight above that floor, and that is the P that acts with the delta in that story. And that will amplify by this factor your deformations. Okay? So in the code, if you compute the stability factor of theta and it's below 0.10, this means that your P delta effects are negligible, and therefore you can neglect them in your analysis. But you have to show this at the end of your whole seismic design, that the deformations are basically below this value of the theta factor is below 0.10 for all cases. Because CBFs are some of the stiffer buildings, unless you get a taller, sort of over 6 to 10 story building, you will not have a lot of deformation compared to other systems. So you can assume as a first assumption that you're going to meet this 0.10 criteria for theta. But don't forget to confirm at the end when you do your detailed analysis that the P delta effects are in fact negligible in this design. Okay, so if we go through this, we got our base shear, which was those values I got at the start. We reduced them because we know we're going to do a dynamic analysis at the end. We distributed them along the height. We amplified them for torsion, and we decided not to amplify them for P delta effects because we thought that the deformations would not be as large. So these are the forces now that we can use for the preliminary design of our brace. Now if you look in ASC, in the document, you'll see that there are a number of loading conditions. There's two that affect seismic loading. Okay, so your combinations are 1.2 times 0.2 SDS, we'll talk about this in a second, times your dead load, plus the seismic effect, plus the live load, plus 0.2 of the snow, or 0.9 minus 0.2 SDS, your dead load, earthquake load, plus 1.6 H. This is basically a water pressure effect. But what's important here is that the code now recognizes that an earthquake is not only horizontal, it's also vertical. So if the ground motion is going up while the lateral motion is at its peak, you're going to get an increase of your gravity loads, and it now recognizes this by the additional 0.2 times, and this is an estimate of your vertical accelerations. Okay? And this here is looking at cases where the seismic load and the gravity loads apply, they act together and they add on. Let's say if you're looking at a column and you're pushing on a frame, gravity loads plus the frame action will add axial load to your column, so you use this. If you're looking at the tension side, when you apply lateral load, you put tension on the on the side of your column, but that basically acts with the gravity load, so you need to look at the lowest estimate of your gravity loads because gravity loads are helping you in that case. Okay, so these are the two load conditions that you need to look at. Now, just so that we don't forget this, these are two of about 7 or 8 load conditions. Okay, so it doesn't matter that you're doing seismic design, don't forget to check all other loading conditions, especially in locations like Boston where the seismic loads are lower. The strength might actually be governed by wind loads. Okay, so don't forget to check these. Just because we're focusing on these, you also have to check these. The other thing is, if you have some structure, you have a huge load in the middle of a span, and you have a concentration of mass, it may be that that gravity load is controlling the loads in your braces. Okay, so careful not to forget the other, basically, load cases. So now we move to the design of the braces. And basically we'll use LRFD and AISC05, and the braces were chosen as ASTM A500 grade B, and we chose circular HSS members, and Jeff Packer will be talking a little bit more about why circular members tend to have a better sort of ductile behavior than square or rectangular HSS members. And obviously, since the design of the strength of a brace is based on its compression capacity, it's quite obvious that using HSS members, if we can connect them properly, is beneficial because it's the most effective way of developing a compressive capacity in a steel member. And so looking at the properties, the steel at 42 KSI, the ultimate at 60, and then these RY, RT factors, which are the material overstrength factors of 1.4 and 1.3. These will also be discussed in more detail later. So if we look at the brace connections, remember we had 3 hinges basically in compression. We need to develop 3 hinges when this brace goes into compression. So this hinge here is pretty obvious, but out here we have 2 choices. Either you connect your brace all the way into your gusset plate and the hinge will happen inside your brace, or you pull the brace out a little bit and you allow the plastic hinge to form in your gusset plate. Okay? Now, if you do the former of the two, meaning that you expect the plastic hinge inside your brace, this connection has to be designed for the full compression force plus the moment, because you form a plastic hinge here in the gusset plate. Okay? Not a very easy thing to do. So very nice detail, just pull this out a little bit, allow a 2 TP distance, we'll talk about that later, and form your plastic hinges inside your gusset plates. These are very stable and they work very well, been shown in tests, whatnot. So the length that we use for our design of our brace is going to be between these 2 assumed plastic hinges and the gusset plate, so that'll shorten the center line distances, the working distances a little bit and give us a little bit more capacity. That's perfectly fine. And we'll use a K factor of 1 for this brace element. Okay, so once this is done, you basically assume that this is a tension compression system, so half the load is taken by your tension brace, half by your compression brace, and you will basically be designing for the compression capacity, which is always lower than your tensile capacity. So the next thing you need to do, going back to one of the first slides, is you need to make sure these braces are going to behave in a ductile way. So first you look at the D over T limits, and you need to choose them such that this R factor of 6 can be achieved. And you'll have a little bit more discussion later, but there's a discussion right now on reducing this parameter here, this 0.044 E over Fy, for the D over T limit by about 85%, and this is again based on more test data that's coming in that we really need to tighten that a little bit more to make sure that we don't have any problems with the ductility of our systems. So this is what was used. We just assumed this just to show that it's not drastic. You could really design this pretty easily, and D over T was kept below 25.82. So then you just go through a typical design at every floor. So the load is basically 51.7 for this one. This is your brace to brace length. We assume a shorter length between the two plastic hinges that I just discussed. Here's a brace member that works. This is the capacity of your member, KL over R, D over T, and these meet the limits. So then you go through this entire building and you design your braces at every floor such that the capacity of your brace is greater than the applied load. Now for Boston, it turns out, as I've mentioned a couple of times, when you check the seismic load condition and then you check the wind loading condition, it happens that the design of every brace in the building is governed by the wind load. Okay? Now what you do is you just use this wind load, you'll size your braces, and then it'll still be a seismic design the same way as if your seismic load's governed, because you still want this building to develop a ductile response even if it was designed initially for wind loads, because the earthquake, when it hits, will yield this system. Okay, so careful to check other load cases. So when we go through the same process for Boston, we basically design our braces, and we again applied load, the length that we use for design with a K of 1, the brace member that was chosen, capacity, KL over R, and D over T. Okay? So now we have a preliminary design of our system, and we need to carry out capacity design. Remember, we have a weak yielding fuse. That's our fuse in our system. Everything else has to be stronger than that fuse if it's going to remain elastic during the earthquake. So there's two things here. One thing is, if you look at this graph, this is the load you've designed for, but your system always has some overstrength built into it, because all braces don't yield simultaneously, and the material that you assume has a certain yield stress will always have some level of overstrength, and so you need to take this into account. So one thing you can do is you can use the overstrength times the seismic load as your loading case here, but really for brace frames what you should be doing, and this really is worth it, is just looking at the maximum capacity that could be developed in your braces and use these forces to design every other element. Okay? So what are these maximum forces? When we chose that brace, we sized it basically on a gross area and assuming some level of the yield stress. But we know that when you order a certain grade of steel, it's likely, when they ship it to you, it won't be lower than that, but it's likely to be significantly or somewhat higher than that lower bound. So what you need to do is you need to have realistic values of these, because if you thought Fy was 36 and your brace was delivered, it was 42, the force in your brace is going to be larger when it yields, and then your connection that was designed to resist this load is basically going to fracture. So you need an upper bound limit, and how do we do that? We apply this Ry factor, this overstrength factor, to Fy, which allows us to get a better estimate of the peak tensile load that we could expect in this brace. In compression, it's important to note 2 points. When the brace first buckles, you'll develop the maximum buckling load. But if you keep on pushing that load, just because of your localized P delta, P small delta effects, that load is going to start going down because you're moving out. So if the compression in your brace is helping the design that you're looking at, you should basically take the lower bound of this value. If the compression in your brace is adding force to the element that you're designing, you should be using the largest value here. Okay, so we'll look at that for some capacity design. So these are the true strength and tension and compression that you should be using in your brace. So let's look at a capacity design case. So if I isolate a beam and I basically look at how I would design this beam, here's what happens. When the brace yields, I'm going to have a GFY in this brace. Because it might be stronger than what I assumed, I apply Ry here. So this is an upper bound of this tensile force. Here, what I'm going to use is basically the lowest value of the buckling load, because these two forces, this one gives me a reaction pointing up, this one a reaction pointing down, this one is much larger than this one, so I need to use the minimum value here to get the worst case where I'm pulling on this beam right in the middle here. Okay? So when you do that, you add your gravity loads, and this will allow you then to design this beam to remain elastic in bending and in shear when the mechanism yields. Okay, so there's no way this can basically fail or yield because these are the maximum loads that these two braces can develop. Okay, so similarly, if we look at the columns, we basically have the same thing. If I want to look at the design of this column here, in capacity design, I have braces on this floor, braces on this floor, and I have my gravity loads here and here. So what happens is when I push on this and I form my mechanism, AG, RY, FY in tension, and either 0.3 PN or 1.1 RY PN in compression, this causes a shear that transfers over here and is then applied on the columns. And in addition, this brace applies a compressive force right into the joint here. So I have to look at both cases. Is it beneficial to this column to assume that the brace has its maximum compressive capacity or its minimum compressive capacity? And you do that on both floors, and that's again how you capacity design the column to remain elastic when all these braces are yielded, buckled. So the preliminary design is complete, and this is what it looks like. We can see the sizes are not that much different because you have two frames in Los Angeles. If we didn't have that, these would be significantly bigger, but still you can see the difference in the section sizes that were found. Now, the last thing you need to do is we need to prove that all these assumptions we made at the start to reduce our base shear by promising that we would carry out a response spectrum analysis are actually done. So with a 2D analysis, you can do this by hand. Brace frames, K matrix, mass matrix is quite straightforward to derive. But you can also use a commercial software like SAP 2000 or whatever program you would use and carry out this analysis. And when we do this, we get lucky and our periods are in fact greater than the two values that we checked, which allows us then to say that the periods of 0.619 and 0.751 that we assumed all the way at the start are okay. Okay? So that is our first check. Our second check is to go through our response spectrum dynamic analysis and compute the base shears. And what we find here is that V design of 340 is in fact another good assumption that we made. So all of the assumptions for reducing our base shear are now through our dynamic analysis proven to be valid. So then using your response spectrum analysis, another advantage of that is it'll give you a more realistic distribution of your forces. And when we go back and check our initial design that we did with the static method, it works pretty much for all the braces, but we do find one brace where the force on that story was a little bit higher through the response spectrum analysis. So we need to redesign that brace. And we do that, and it changes we change the section to 6.625 by 3.375. And then we repeat the response spectrum analysis with the new brace. It doesn't change very much. And then we get a design that is finalized. Now, the last thing is you need to check displacements, okay? And all the way back at the start, we talked about this equal displacement rule. So the way the code asks you to check displacements for a seismic response is the following. You apply your reduced seismic forces, so your VE divided by the R factor, and because you are designing in this area here, your elastic model is valid. Okay, so the deflection you compute by applying your reduced seismic forces is a true calculation. There's no approximation to that. And then what you do is you take this computed displacement delta and you multiply it by the factor CD that is given for this system. And if you remember back, CD was equal to 5 for brace frames. So if you found a displacement of delta, 5 delta would be your estimated inelastic maximum displacement. So the displacements are used for two things. One, you have to make sure you don't basically surpass the limits that the code has on deflections, 2% of the story drift, etc., depending on the type of building. But also, And here are the deflections that we get by doing that. 4 inches at the top here and 1.144 for Boston. And the next thing you need to do with your deflections is make sure that that P delta effect assumption that you made at the start is actually valid. So you go back, you sum up all of the gravity forces from level 5 to 1. You have the displacements here in inches of that story. You get the shear on the story, the height of the story, and then you can apply and check this stability ratio theta to see whether it's under 0.1. And in fact, they all are under 0.1, which is often the case for lower brace frames because of their stiffness. If it's not lower than 0.1, it's not a problem. You'll amplify the displacements and the forces for P delta effects. Okay, but in this case, you can get away with it, and the same goes for the Boston design. So once all of this is redone, here is the final design of the 2 frames in Los Angeles and in Boston. Okay, so I'll hand it over now to Jeff Packer, who will talk a little bit more about connection details and issues on HSS response and new connectors for seismic design.
Well, after that commercial break, we'll carry on with some connection design now. And in the building in LA and in Boston, you remember the building in Los Angeles had a much higher base shear, but within this actual building on the 2nd floor in Boston or the 5th floor in LA, we actually have the same hollow structural section, 5.563 by 0.258, and note the way that's expressed for circular or round hollow structural sections there, according to the designation. And that means then when we come to do connection design, the connection design is just going to be based on the actual member. So there we have the same member, so therefore we actually have the same connection design, ironically, in both of these places. So the connection has to be designed for AG, RY, FY, where we have the gross area multiplied by this overstrength factor RY, multiplied by the yield stress, and it's 42 KSI because we're using ASTM A500 grade B HSS. So we have the same connection requirements at these 2 places because we've basically got the same member. So just to recap on this RY, RT stuff again, RY is the expected yield stress relative to the specified minimum yield stress. RT is the expected tensile strength relative to the specified minimum tensile strength. And that's basically, as Constantine explained, that the steel will be delivered over strong in all cases. They'll exceed the minimum specifications, and so you do want this material to yield. That's the basis behind the whole design process. So therefore you have to actually design the connection for these enhanced forces. Well, if we go to the AISC seismic spec in 2005, this particular table, and take out the RY and RT factors, we can see that they're different for different types of products. But they're the same for ASTM A500 grades B and C, interestingly enough, and we have an RY of 1.4 in this particular case. ASTM A501, which is a hot form product, is now back in the market again. And it's also assumed that we have the same RY value for that at the moment, but these are in great debate in technical committees. RT represents how much the ultimate strength is likely to overshoot, and these are again different values. Now it's odd that of course we'd have the same overstrength factors for various types of materials and different grades, because if we look at modern production methods and a typical material test certificate that we see now, tube companies are largely making on a one grade fits all sort of basis, because they don't want to basically have lots of different coils for different grades, for grade ASTM A500 grade B and grade C, so they would buy one coil to suit them both. So we get what's called dual certification at the moment. So those RY factors were actually based upon a study assuming that the product was grade B, but actually it's usually always made to also be grade C. So those RY factors are in fact very conservative. Now, but we still will have to adopt and design for those at the moment. Now, when we come actually to design the connections, one major issue is that is how you actually design the brace at the actual gusset plate. A very common way of doing this is to actually put a slot in the end of the circular tube, slot the gusset plate into that particular slot, and sight weld the tube to the gusset plate with fillet welds. This is a carryover from a very popular sort of bracing design that's used for wind bracings, and so it's been applied everywhere for seismic connections as well. Well, when this is done, the tube is usually over-slotted, which means then the slot is made slightly longer than the insertion length of the plate, which means you'll have a small gap at the end here. So there will actually be a hole at the end of this connection here. So that's right at the very, very critical place where your connection is likely to fail. And you've reduced the cross-sectional area from a gross area down to a net area. And then, due to this phenomenon called shear lag, because you're only applying the load into this brace member on two sides, it's being applied on one point of the circumference by the plate, and then at 180 degrees around the tube at the other point, we have the tube non-equally loaded. It's highly loaded on two parts of the perimeter and unloaded on some other parts of the perimeter. So therefore, the shear strains in part of the cross-section lag the shear strains in other part of the cross-section, so we have a phenomenon called shear lag. This then tends to reduce the capacity of the cross-section as well, and makes it prone to fracture across this critical cross-section here, which is shown on that diagram. So that's one of the key things we have to check for, assuming we're going to join in this very popular manner here of just slotting the plate into the hollow structural section. So we have to cut a slot into the hollow structural section. Fabricators like to just burn this out fairly roughly, as shown on the left-hand side there. It's very popular, and the question often arises, can it be left rough cut like that? Well, it doesn't matter if it's a wind bracing, really, because that's a statically loaded building, or quasi-statically loaded building. But once we get into dynamically loaded structures, where we've got fatigue loading or any type of dynamic loading, high cycle fatigue or low cycle fatigue, seismic loading, then you should really have these cut very carefully around the ends. So because the cracking will start at the termination of the weld here, the weld transfers the load between the plate and the tube, and so the load is transferred especially at the end of the weld here, and so cracking will tend to will start at this particular point here if the connection fails, and go out here and then tear out down here, or it'll run around the cross section here and fracture around the cross section there. So that's the critical point that you have to worry about, and keep the cut quite smooth at that point. So we're going to design this connection as a field welded slotted HSS to gusset plate connection. By field welding, you can essentially plumb the frame and have the gusset plates connected into the actual building frame, then bring the bracing member in, put it into place, and then fillet weld it correctly as you'd like it after it's as the final stage. And we'll be focusing on the plate to the hollow structural section connection, and that's because that's where we find the critical shear lag problem. For plate material, we'll just use A36 material, and the calculations that I'll follow through here will actually be what the engineer is required to design the gusset, to design this plate to HSS connection, but I won't actually be covering the design of the gusset plate. There are many particular other issues that have to be addressed there, such as block shear rupture in the gusset plate, tensile yielding of the gusset plate, buckling of the gusset plate, and also how you actually transfer forces to the beam and the column as well. So we'll just run through the plate to HSS connection today. So the two key failure modes that I've been talking about are this fracturing of the hollow section around the circumference here, the circumferential fracture, which is induced by shear lag, starting at that little open notch at the end of the slot, or you could actually have shear rupture, where you actually tear out the plate all the way along the sides of the welds here. This one on the right here is more likely to occur if the insertion length of the plate is small. The longer and longer the insertion length, the more plate you push into the tube, the more you avoid this type of connection failure, and then if you push it in further and further, the shear lag problem as well is reduced over here. So long plate insertion lengths certainly reduce connection problems, increase the connection strength. So let's design the brace to gusset plate weld to start with a fillet weld, and we'll aim to develop the maximum we want to determine the maximum fillet weld size by setting the weld strength less than the shear rupture strength of the hollow structural section. The shear rupture strength of the hollow structural section is the phenomenon on the right there, and if we're going to make the weld more critical, we're basically avoiding the failure mode on the right there. So we can solve for D, which is the number of 1/16ths of an inch in the actual weld size, the weld leg size, by dividing the shear rupture strength of the hollow section in the numerator there by the weld capacity per inch, and we'll find that our upper limit on D is 4.66/16, so let's pick 4/16 then. We have to be under that to make sure this failure mode governs over the shear rupture. So with a 4/16 or quarter-inch longitudinal fillet welds with E70 electrodes with an ultimate strength of 70 KSI, we can then calculate what the required weld length is. Now, we still have to develop that maximum brace force, that over-strength force in the brace, which is the yield force in the brace multiplied by Ry. And if we calculate that, it was 235.8 kips. So that's the force that must be delivered, or the required force in this particular connection, and then we solve for L required, the length of weld required, and it comes out to 10.5 inches. So finally we'll pick a weld length then of 11 inches down the bottom. Next, let's size the gusset plate based upon the criteria that we're looking at for the gusset plate to tube connection. Again, we have to develop this overstrength force in the brace, AGRYFY, which is 235.8 kips. And so now, again, to avoid shear rupture, if we divide this by 2 times phi, which is times 0.6 FU in the gusset times the length of the weld here, we can solve for the actual minimum thickness of the gusset plate, which is only 0.4 inches. Now, that's not an available size. We'd round that up to some particular gusset plate size, like 1/2 inch, but then we're not actually going to go and look at these other gusset plate failure modes, like buckling of the gusset plate, for example. So when we do that, we'd find that we'd actually have to move the gusset plate thickness up a little bit more again. So we'll actually pick a size of 5/8 inch here. So what we've essentially done now is made sure that the tear-out strength of rupture strength of the hollow structural section is greater than the weld strength, which is 245 kips if we were to calculate it based on those calculations, and that in turn is greater than the required tensile strength of the connection determined by a ductile yielding failure mode, which is the AGRYFY 235.8 kips. So the lowest governing force is actually a ductile failure mode of AGRYFY. All the other connection parameters have a strength that exceeds this. So that's what we're aiming for. Now we have to worry about the shear lag problem in the brace. Remember, that was the left-hand picture of those two, whereby we got circumferential fracture around the hollow structural section. This is essentially a brittle connection failure mode, which we want to avoid as well. So the strength of the connection for this particular failure mode must be greater than the actual ductile failure mechanism of yielding of the brace, with the overstrength factor again, the AGRYFY. So the fracture strength by this circumferential fracture mode is phi times RTFUAE over here, where AE is the effective area at that critical cross section, right where at the end of the slot And when we then put these numbers into the equation here, we see that we're actually doing a capacity check with a safety factor in here, essentially a resistance factor of 0.75, but we're multiplying by an overstrength factor for the ultimate of 1.3. This comes out to about 1 anyway, so these are essentially self-canceling, really. So we've got the ultimate strength of the brace material, 60 KSI, multiplied by the effective area at the critical cross-section, which is the fracture strength, greater than the yield strength, the yield force that's going to be developed in all likelihood in the brace. So we can solve for the effective area required, A sub E, and we get 4.03 square inches. Now, that means that at that critical cross-section where we've got that little knot, that slot, we need an effective net area which is actually greater than the gross area. The gross area of the tube is only 4.01 square inches. So we need a cross-sectional area to avoid this failure mode which exceeds the gross area of the tube. Problem. So we've obviously got to put some sort of reinforcement in. Now, to reinforce it, we've got a circular tubular member now. So we essentially have to increase the net area at this particular location. So we'll use quarter sections of the same HSS brace, 5.563 by 0.258. So we'll cut the tube into quarters, basically stretch out that material, and because it's actually exactly the inside diameter of that reinforcing material is not going to match up with the outside diameter of the actual tubular member because we're cutting it from the same member, but we can stretch this and patch it onto the outside of the brace. If we do that, we end up with reinforced connections that look like this. Here's the type of connection we're talking about, where we've got a slot in the tube, the plate pushed down the slot but not going to the end because it's over slotted. There's the critical net section through there, and on this left-hand picture here we've got a circular tube with a patch on it here, basically as a quarter tube, which is basically our reinforcing plate, and this is the way it would end up looking. And if we did the same thing on a square hollow section, we could put the patch plate on just on two of the four sides, on this side of the square hollow section and on the far side of the square hollow section as well. So then you can see that when you get your critical cross section through here that's liable to fracture, or through here, then you'll have actually increased the net area at this particular location. And here you can see the popularity of using square hollow section braces over circular hollow section braces for these seismic applications, because when you do reinforce in this manner, you put the patch plate, the reinforcing plate, onto a flat surface, and you can, if you keep it, if you keep the plate width within the flat width of the square hollow section here, you can actually just fillet weld along the edges here before you actually encounter the corners of the hollow section. Here, more complicated of course, because you have to have it sitting on the round of the circular or round hollow section. So that's what would end up looking like after we've reinforced it. To figure out the effectiveness of this reinforcement, we need to find the location of the centroid of the cross-section of the reinforced area. So basically we now have a circular hollow section here with a gusset plate sticking into it here, and we have a quarter section added to the top here, a quarter section added to the bottom here, and there's a procedure in the manual which essentially is spelt out for you, which you can follow for actually finding out where the centroid of this steel material on one side of the plate lies, because it's the location of the centroid of all of this half tube here with the reinforcing tube on top, which will affect the shear lag that's going on in this particular connection. So this distance from the flat surface here up to the centroid or center of area or center of mass of the steel on this one side is called X bar, and that will be defined by this procedure over here. So essentially it's a first moments of area concept that is used. If we go through this and solve and calculate for X bar, of this total half cross-section, we can get an X bar of 2.205 inches. Now when we do this, to actually put the gusset plate into the slot, you have to have a certain slot size, which is going to be slightly larger than the actual plate width as well. So if you go perhaps 1/16th slot width above the actual plate size, which I've assumed here, which is very small, then the plate could potentially end up being fabricated across to one side of the slot. So then you could get a 1/16th gap at the root of the fillet weld on the other side. Well, AWS D1 allows a 1/16th inch gap to be overlooked in terms of actually sizing the fillet weld, so we'll operate on this basis here. We'll assume our maximum gap is only in the root is only 1/16th, so we don't have to go back and resize that particular fillet weld. So now, having solved for this X bar, the centroid of this half cross section on one side of the plate, we can use this U factor of U is equal to 1 minus X bar over the length of the weld, X bar over LW, to calculate what the U is, which is the reduction factor due to account for shear lag. And we get a value of 0.8. So that means then the cross section where at the end of the gusset plate is only 80% effective, and there's about a 20% loss in effectiveness there due to this shear lag phenomenon. Now, if you looked in the specification, AIC spec, you would note for unreinforced connections, you would find a little note that if for slotted plates into round HSS, if the length of the weld exceeds 1.3 D, then the connection is 100% of effective and has no shear lag reduction. And we're up to actually 1.98 D in our insertion length, much beyond that. So the chances are we have no shear lag reduction here as well. But this little rule here was determined for unreinforced round HSS, and we've now got a reinforced HSS connection, so it's a different animal really. So we will still stick with this shear lag reduction factor here, which is a slightly safer approach of using 0.8. So we apply the 0.8 reduction factor to our area that we've calculated up here. This is of 0.8, and then we've got this area of the tube on two sides of the gusset plate, so we double it up and we get an effective area of 4.55 square inches at the critical location, which is more than the effective area that we required. So that's fine. We will not have this circumferential fracture phenomenon due to shear lag occurring. Next, let's design the welds from the reinforcement or cover plates to the hollow structural section brace. Well, here we must also, when we're doing this, bear in mind what the real thickness of the hollow section cover plate is. Remember, when we're using hollow structural sections to ASTM A500, we have to use the design thickness, which is actually 93% of the nominal. So the real design thickness minus 1/16th would be the maximum leg size that you could have on your fillet weld along the edge of that cover plate, which is 0.178 inches. So let's go a bit lower than that, pick a leg size, a weld size of 1/8 inch, which then, having set the weld size of the cover plate, would prescribe the actual total length of the weld that we need. So using that approach, we solve for the length of the weld then we need. We don't want the cover plate to fracture. So if we actually have the fracture force of the fracture load of the cover plate, again, using our phi factor with an RT factor in here, again, these are self-cancelling approximately, and these will come out to about 1. And then, so we've got the ultimate stress of the tube material, the cover plate material, multiplied by the net area of that cover plate, which is actually the cross-sectional area of the cover plate, divided by the strength of the weld. We can solve for the length of the weld we require, 10.5 inches. So that's the minimum length of the weld, assuming we have a weld size of 1/8 inch. So we've designed the connection then for the tube to the gusset plate. And these are all the factors that we'd actually have to check. Next, we would carry on with more checks for the actual gusset plate here, which may affect our gusset plate sizing. Note that we've got this 2T gap here as well, so we can develop the plastic hinge in the actual gusset plate. And this is a very active research area at the moment. There are many different ideas on how to actually shape and proportion this gusset plate for even improved hinging here. But basically, one rule is not to over-design the gusset plate. Keep the gusset plate moderate, relative, as thin as you can, really, because then you won't transfer such large forces into the neighboring beam and column here. Now, I mentioned that, and Constantine had mentioned that circular hollow sections are a likely better choice for this brace than a square hollow section, or a rectangular hollow section as well, but certainly they're more optimal than a square hollow section, which is the common alternate. And the square hollow section, as I mentioned, is largely popular because it's easy to reinforce. If we looked at a square hollow section brace test, which we see down the bottom here, this is one which has got the open slot at the end here, at the end of the gusset plate, the type of connection we've just been designing, and you can see the patch plate on the hollow section here, which is easy to apply to a square hollow section. But cold form square hollow sections to ASTM A500, as available in North America at the moment, have limited ductility in the corners because there's a large amount of cold working that goes on in making these sections. So in the corners here, you have a fairly reduced ductility. Fy, in other words, gets up fairly close to Fu. So once you have yielding in the corners, it's close to fracture. So this type of brace tends not to be able to survive all that many cycles under cyclic loading. So we see that now the Seismic Committee of AISC TC9 is actually proposing at the moment to have an advisory posted on the AISC website this year, which will be pointing out these essential aspects here. One, whenever you have slotted end HSS brace to gusset plate connections, they should be reinforced at reduced sections. And we've just gone through the rationale for that by these calculations to show that whenever you have a reduced cross-section, an open slot, open gap at the end of that slot there, you'll need reinforcing. The permitted cross-section slenderness is of the actual cross-section, the B over T's, that's the flat width of the hollow section divided by the thickness, and the diameter of a circular or round hollow section divided by the thickness, the D over T, are going to be reduced even further beyond the current seismic limits. If you can keep essentially the members fairly stocky and the overall slenderness of the brace relatively high, the KL over R perhaps around 100, then you'll get probably maximum survivability of the brace. And then the brace connection to the actual frame, you have to now, it'll be pointed out that you must take into account the transfer of actions into the neighboring beam and column so that you also don't get overstressing and potential failure of the beam or column connections as well. So this is an advisory that's going to be posted relatively soon after it goes through the AISC committee structure. So how can we avoid some of these connection problems? Let's just have a look at some new seismic connection research. There's one cunning idea that, well, if you want to have a slotted connection and you don't want to actually stop the welds at a critical net section, then why not stop the welds for a slotted connection at a gross section? So you could actually slot the gusset plate as conceptually shown here, and slot the tube, and then poke the gusset plate into the tube like this, but they actually overlap. And so then where the actual plate stops and the weld goes to the end of the plate, then the weld will be actually stopping at a gross section. Well, very clever, you say. That's very hard to fabricate because you'd actually probably have to push the two together and then pull them back a certain dimension to actually get this the right hidden gap, as we call it. Anyway, this is one potential way around it, which is basically sort of like an advanced detailing procedure. Or perhaps you could just not reduce the gross area to a net area by using a connector which connects on to the gross area of the tube. Now, there's one concept whereby you can, being advocated, whereby you can actually make a connector by using casting. So it's out of cast steel, a ductile material, which connects onto the gross area of the tube, and it's pre-engineered essentially for all different types of seismic loads. And this is actually being marketed by a company. It's actually here at the convention as well in aisle 500, Cast Connects. So this is basically then a solution where you don't have to be an expert in connection detailing, and the connector will remain elastic. The hinge will occur in the center of the tube up here, and also down here in the gusset plate here, and the concept is that this part of the connection here is essentially elastic and is pre-engineered for you. So this is what these types of cast steel connectors look like. And the concept is that this you can actually obtain one casting of a certain particular size with a nose on it, and then are made for round tubes, and then a round tube of one particular diameter, say 6 5/8 inches as shown here, would then be pushed up onto this nose of the casting, and the thinner the actual tube is, the further it rides up. The thicker it is, the less it rides up on this particular nose here. And then one joins the round HSS to the casting with just one weld, a complete penetration weld from one side. So this is very straightforward and doable by practically any fabricator. Advantage of this is you know the actual cost of this manufactured connector. You know the cost involved in producing this seismic resistant connection, whereas it's a very skilled art to go through the procedure we've been talking about before. The castings are made to a popular casting grade, which is actually weldable. And for a particular tube size, these tabs that stick out at the end here are fairly long and can be cut off by the fabricator depending upon the actual force that you need to develop the AGRYFY in this particular member, and the fabricator would also determine the actual number of bolts needed as well, and bolt up accordingly here. So all you need to design is for the number of bolts. So here's a cross-section from an actual HSS to casting that's been sectioned through and polished afterwards, and you can see what the resulting effect is with this full penetration weld here at this particular joint. These have gone through laboratory validation and testing as well. I think we had this picture on the left before, but this shows the huge amounts of displacements that these tubes can go through if you keep the tube relatively thick and stocky, keep the overall KL over R long, up around 100, but certainly over 70, and then on these tests on the right-hand side here, where you see we've got a more punishing situation with a lower KL over R deliberately, we've actually yielded the tube in tension here, and all the whitewash has come off here during a tension loading cycle, but you'll notice that the whitewash has not flaked off here around the actual connection because it's actually remained elastic, which is the aim of the game. So hinges occur in the gusset plate up here, and in the middle of the tube, and in the gusset plate down the bottom as well. So you have a sort of an instant problem solved for you. The outcome is then a connection which could look something like this with a casting. Here we see the tab clipped off and a different sort of bolting arrangement. The casting comes without the bolt holes, so the steel fabricator actually picks the bolting arrangement here, and the connection ends up being much more compact than a competing connection would be over here. Here it's done in a round hollow section. Here's the competing section done in a square hollow section, because the fabricator would prefer to put the patch plate onto a flat surface here. As you can see, much more complex, much more detailing, fairly simple over here. Here we also see the gusset plate bolted on to the neighboring column as well, which provides more ductility in the connection. Finally, with regard to developments with regard to this cold form tubing product in North America, It does have its limitations at the moment. We see that it's the subject of some advisories from coming out from AISC. So there is actually a new tube product specification under development at the moment. In fact, the AISC committee met on Tuesday, and this will be going forward through the ASTM specification process shortly, and so we should end up with a new higher performance hollow structural section specification for North America, which will be ASTM A1000 and something, I'm told. So what will this new type of tubing look like? It'll still be cold formed tubing as made conventionally at the moment in North America. But the aim is to have tighter thickness and mass tolerances, so therefore we can avoid this 0.93 T design thickness that we have to use with conventional current cold form tubing. So that it'll be made to the nominal specifications. Have larger corner radii, which will get around some of the cracking issues and ductility issues in the corners. Have a minimum yield strength of 50 KSI. I mentioned before that the tubing is largely made to a one grade fits all approach at the moment, and we actually get dual certification. So everybody else in the world is making to about a minimum strength of 50 KSI, so this would be the minimum structural grade. ASTM A500 would still be available, but this would be a preferred grade for structural and especially dynamic applications. Fourthly, we'd have an upper limit on the yield stress as well of 65 KSI. This basically puts the tubing into the same ballpark as ASTM A992 for wide flange sections as well. Makes it ideal for seismic applications. There'd be a notch toughness requirement provided as well. This would be 20 foot-pounds at 0 degrees F. So that means that we'd have a tough steel provided for the first time, and the nominal FY to FU, yield to ultimate stress, will be limited as well to something around 0.8, and as noted in 0.7 there may be also the concept of introducing Class C and Class H finishing as well. So basically this is something that's done in Canada, and this would then enable this specification to be referenced in Canada as well. This means that the normal cold form finishing is what's called Class C, and Class H is basically heat treated, not normalized, but heat treated to reduce the residual stresses. And greater regulation of the chemical content as well, lower carbon and lower silicon especially. So these are some of the attributes of this new generation tubing, which we should see on the market relatively soon after the specification is finalized. So I think that finishes the presentation, and the floor is open for questions.
You're going increasing your FY, isn't that going to start increasing on the connection sizes as well? Your FY, AG?
Oh, it will, but then it'll increase the whole capacity of the usefulness of the members as well. So obviously you're making the whole steel structure more efficient if you push up the FY. FYs now are typically running well over 50 KSI as delivered anyway. So this kind of reflects what is really being delivered, and then the RY values can probably be brought down to something a little more realistic. Well, first of all, those pictures are not actually of the actual designed example done here. They were just typical fabricated, typical reinforced braces on the shop floor. But yeah, the reinforcing plate is going to have to be 90 degrees circumferentially away from the slot.
I don't think that's how it showed it in the photograph. I mean, I might have
It, yeah, it was basically you'll have the plate going into the tube here, and you'll have the cover plate on a remote area of the HSS. So essentially, when you then take the cross section all the way through, you'll be adding up that area into the calculation. On the round HSS, it wasn't as obvious to see that cover plate, I think, as on the square HSS. Yeah, so I picked 4/16 instead of 4.66. Basically, it's if you, it's just a clever little ruse, if you like, to actually avoid one particular, basically by making the weld strength less than another failure criterion, which was that shear rupture strength of the picture that was on the right-hand side, if you remember that one. So basically, there's a hierarchy of things you have to solve for. If you have to meet, you have the lowest force, the critical failure mode has to be AGRYFY, the force in the brace, right? This was around 236 kips. Then everything else has to be basically providing a strength or a capacity above that. The weld, the circumferential fracture, taking into account for shear lag, and for the shear, the tear out fracture as well. So this was just playing around with two of those failure modes, just dispensing with one and tossing it off by making the other one more critical. It's probably more obvious if you set them all out and say failure mode 1, this is the strength, it's greater than AGRYFY. Failure mode 2, this is the strength, it's greater than AGRYFY. Failure mode 3, or the weld, it's greater than AGRYFY. So we're just playing around with a couple of failure modes just to dispense with one so I didn't have to do the calculations. This is actually done quite frequently in the manuals, you'll find, which is a little bit tricky, I think. A little bit too clever, probably. Yeah. About the R's 3? Constantine, do you want to? Come on, you can come up here.
Sir, if I understand your question was why go to an R equals 6 system, which is what we've been discussing today, rather than go with an ordinary brace frame? Is that? I guess we used an R of 6 in the system we did, and if you basically use an R of 3, you're basically going to design for twice the seismic loads. So every single member in your structure will be designed for double, which means all your diaphragms, foundations, columns, beams, everything that is not part of the yielding system. So there's one reason why you would want to go towards a ductile system. And in reality, I think we're going to see a lot of changes coming out. There's a new document now where people are going to be assessing collapse of structures to assess their safety. If you have a ductile system, I think that it's very clear that based on the incertitude related with the ground motion, if you're hit with a larger ground motion than the one you designed for, you will have some built-in ductility, which will save the structure. If you've designed a minimal ductility structure, yes, for the design level earthquake, it's probably going to be okay. It's not a problem. But if you get a greater earthquake than that, then it's basically at risk because it doesn't have this ductility built in. So in terms of the economics of it, yes, you might get away with a less expensive frame if you do it for R equals 3. Not necessarily, though, if you look at the whole thing, because your forces are reduced greatly when you use R equals 6. But really, in terms of the safety of the structure you're designing, I think, in my mind, there's no doubt that if you design ductile structures, you're really going to get a much better response. Yep.
Basically, there are many different grades of cast materials, and there are a couple that are, or several that are actually recommended for casting applications. This one is if we can just get it up here. I think it's close. Here we are. It's ASTM A958. and it's a class 80 fit, what they call class 8050 material. So it has a very similar composition to ASTM 514, and this is a pre-qualified weldable steel grade. So this is one of the grades basically recommended by ferrous casters, and also we've been working in conjunction with the Steel Founders Society of America here. Dave Powlight is in the front row, and he's been particularly helpful in advising on the right sort of grades that be appropriate for structural steel performance. So this gives you essentially the same performance as the steel in the structure.
Just a question, when checking for importance of P delta, do you take spectral deformations or you use the equivalent static deformations? Because spectral will not give us the maximum difference.
No, when you're going to carry out your analysis, it's only going to be checked on your final displacements, which are the ones coming out of your response spectrum analysis. So in the static method here, we just assumed that we would be below theta equals 0.1, so we neglected it, but the final check is based on your spectral displacement. So because the spectrum is reduced by the R factor, you're going to get elastic deformations at the point of first yield, and all those deformations are amplified by the factor CD of 5, and that is an estimate of your peak inelastic deformations. But this is done through the response spectrum analysis. If you're going to carry it out, your displacements are going to be there, so that's a much better estimate of your displacements than just using the static method.
The difference between two stories is not in the maximum one.
Well, that's why when you do your response spectrum analysis, if you do it properly, you do not compute displacements using SRSS combinations and then compute your interstory drifts. What you do is in each mode, you compute the interstory deflections, and then you combine using SRSS the interstory deflections to get a prediction of your maximum interstory drift. So that's the proper way of doing it. Otherwise, they don't occur at the same time, right? When you do response spectrum analysis, you lose the time of occurrence of the maxima, and therefore you need a statistical combination between the modes in order to estimate the peak response. But you're right that you have to do it for the interstory deformation per mode and then combine them statistically. Oh, okay. Well, I guess the question was what happens when you fill your brace members with concrete, and that adds significant stiffness, and that there wasn't a lot in the specifications to help a designer take that into account. And to answer your question, I'm not really sure how you would do it. You're right that it probably would stiffen the member, and
some guidelines on calculating stiffness of concrete flow tubes, but there are several ways of doing it, and they're not very explicit on which way you should do it. It's left a lot largely to judgment.
okay.
Well, thank you.
Thanks.